Welcome to AI for Good, the leading action-oriented, global and inclusive United Nations platform on AI. Organized by ITU, in partnership with 40 UN sister organizations, and co-convened with Switzerland. The goal of AI for Good is to identify practical applications of AI to advance the United Nations Sustainable Development Goals and scale those solutions for global impact. In today's session, we're counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished panelists and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Thank you so much, Hannah, for the nice introduction. Good morning, good afternoon, and good evening to everyone joining our session. Welcome to the AI for Good Machine Learning 5G Challenge webinar session. My name is Thomas Pascal from ITU, the International Telecommunications Union. The Machine Learning 5G Challenge aims to create a community to solve network-related problems using AI and machine learning. And today I'm very excited to host a webinar. This is to launch the second problem statement of the 2023 ITU AI and Machine 5G Challenge. And this webinar is titled Digital Twin Enabled 6G Depth Map Estimation in 6G mmWave Systems. So as always, we are counting on you, the people that are joining in this webinar, to engage in this discussion. If you have a question, please type them in the video wall, and as well as you can send a comment on the video wall. We will take them during the Q&A session after the talk. And I would like to introduce today's speakers. So we have Steve Blandino from NIST in US, as well as Yeswath Gudeti from Samsung R&D. This is in Bangalore, India. And they are going to discuss on how to apply machine learning techniques to outperform the baseline solutions in order to shed light in millimeter wave propagation in real-world environments, as well as tackle the challenge of future wireless systems. So I would like to welcome Steve. Steve, good morning, and thank you so much for taking time to be with us. I know it's early morning in your time, so good morning and welcome.
Good morning. Thanks for having me and actually for having us today.
Yeah, so the floor is all yours. You can take it.
Yeah, thank you. I'll share my screen. All right. So the topic of today is basically the presentation of the new challenge. It's basically about estimating the map of the environment using millimeter wave communication system. This is not a new challenge. We had a similar challenge last year. We had a good experience, and we had actually a good solution from Samsung R&D Institute. So during the year, we have teamed up with Yeshant and the rest of the team, and we are providing a new challenge this year, basically trying to estimate the map and beat the solution that was provided last year. So the talk is basically divided in two parts. In the first part, I'll reintroduce the problem statement, shed lights on the measurement system that we have, the measurements that we collect. And then in the second part, I'll hand over to Yeshant, and he will present the machine learning solution. Just a little bit of the context we are operating. We are discussing about wireless sensing using communication devices. Basically, in general, wireless sensing is the process of acquiring environmental information with different sensors. We don't specify the sensor, and the technology can be using camera, radar. But what we are trying to use now is to use communication devices. It's basically the new branch of research under the umbrella of integrated sensing and communication. We use the wireless communication signal and using the advancement in computing, in machine learning, we try to enable new use cases. We try to enable wireless sensing using basically a device, everyday device that is equipped with a radio. So integrated sensing and communication brings different advantages, let's say, because integrating sensing and communication allows to reduce cost because we can reuse the same device to perform different tasks, reduce the power consumption, so increase the power efficiency of future networks. Those technologies were fighting for spectrum in the past. Now they are basically, we can design together to reuse spectrum, and we enable new applications. So for in 6G networks, ISAC will enable new application. For example, in healthcare, we can monitor vital sign just using communication signal, for example, heart rate or beating rate. We can avoid car accident just detecting sleeping behavior in the car, and then we can detect person in the room. But what we are really interested in this challenge is about environment, trying to understand really the surrounding around us and mapping the environment. So we use already waves to see the physical world, let's say, and we have a lot of experiments, measurements in the literature, but also we have done something on our own here at NIST, for example, detecting a human person walking and trying to understand the characteristic of the target, for example, its velocity over time. So this is something that we somehow know how to do. What we are trying to do now is use the communication waves not just to see the physical world, but also to create a digital world, to create a digital twin. Basically, the idea is to start from a physical representation of the world to the physical world and use the radio communication signal together with techniques, artificial intelligence, machine learning techniques, to represent the physical world in the digital domain, have the same representation but digitally. And what that allows is basically is to find solution to several problems in the digital domain. So once we can apply a certain technique in the digital domain, for example, we can do simulation, verification, prediction of a certain phenomenon. We'll see an example in the next slide. Then we can have an inference and apply the solution that we found in the digital domain and apply it on the physical world. So the example is one classical example, one classical problem at millimeter wave communication. So basically, you know that because of, let's say, narrow, small antenna aperture at millimeter wave, we have to use antenna arrays, and antenna arrays comes basically with narrow beams. So if you have a transmitter and a receiver that are communicating with narrow beams, they need to align their beam. So there is a beam selection procedure, and basically this works scanning different beams over time. So there is, for example, the transmitter that is searching where the receiver is, and the receiver is listening in omnidirectional mode. And this is basically the traditional beam selection that we do at RF. So scanning a lot of beams over time. And that's pretty time-consuming procedure. In the past challenges, also we have seen different methods to improve and to make this procedure more efficient. For example, using sensor networks, using, for example, camera, LiDAR, radar, and out-of-band information, let's say, to aid the communication and to aid the RF to find more quickly the beam. What we are trying to do here is slightly different. It's basically trying to digitalize the environment. So in a way, the transmitter and receiver knows exactly the surrounding, and then do, for example, the same beam selection procedure that we used to do in the physical world using a beam scanning. Probably we can do it in the digital world without really wasting so much time in real life. Find the solution in the digital world, in the digital twin, and then apply it in the digital world, in the physical world. So here we are dealing basically with multidimensional information. We have sensor network is the classical approach to acquire multidimensional information. For example, using camera, LiDAR, and other sensors, we can get very high precision multidimensional data. However, we need more hardware, more power, and is not very scalable over large network because we really need to build a lot of sensors. So what we try to do here is to use integrated sensing and communication. So replace the sensor network and reuse as much as possible the RF signal to give us the same information that a sensor network would provide us. So this is good because we can acquire a large source of data and we reuse same hardware and spectrum. But of course, there is some extra processing required to acquire and process those multidimensional data. And that's where machine learning can help a little bit to relieve the processing required. But still, the sensor networks is not really replaced, but actually it's helping us realizing this project of using just the integrated sensing and communication network. Because what we can do is basically to design our AI ML model by, let's say, training our model with our RF data that are used also later for inference, but we need some guidance, some labeling this RF data with our sensor network. So the idea is to use all the data that we have to train a AI ML model, and then just use the RF to perform the prediction. So for this reason, at least we have basically collected some measurements, and the measurements are collected with multiple sensors. So we propose here measurements in an indoor environment. This is a conference room. We have different tables and chairs, and the walls are made of different materials. Basically, you have glasses, windows. So the propagation of the wave in this environment is pretty difficult to describe. Let's say when we analyze the data, we see reflection from everywhere, from the TV, from even the projector. We can see multiple components, let's say, bouncing off that. So the measurement campaign was conducted with a fixed transmitter that is somewhere here. and the receiver is actually moving on different trajectory. So we have three different trajectories, trajectory 1, 2, and 3. And we provide all the data from area 1 and 3 that are will be used in the challenge for, let's say, training the model and validating the model, and then area 2 will be used for evaluation of the model. So it's not fully available. So the data that we collect is actually RF data, LiDAR, and cameras, even though in this challenge we use only RF data and LiDAR. However, photos are also available. So this is the receiver. It's mounted on a robot, and you can see the top part that is zoomed here is basically what we define it as a tree system. It's an antenna array in which we collect RF signals and we extract multipath component. Then we have a 360-degree LiDAR and a 360-degree camera. So with this data, we design the following challenge. The idea is to use two MIMO nodes, one transmitter and one moving receiver. And we observe the environment changing over time because we see different, basically, data at each different time that the receiver is moving. So basically, the receiver is moving in position and orientation, and each capture has a different observation of the same environment. So the challenge is basically to estimate the depth map of the environment at each receiver position using the RF signal. So going into the details of the MIMO signals that is used, let's say, for inference, for understanding the position, we use a 8x8 antenna element, a transmitter and receiver. And this is an example of channel impulse response of one single element to one single element, so a SISO impulse response. And you can see clearly the different multipath component that you have in the environment. And another point is that the channel impulse response is sampled at 1/1.76 nanoseconds, which is the conventional sampling rate of WLAN, millimeter wave WLAN systems. So the idea is to use this MIMO channel as input of our machine learning model and to have some prediction that is the basically the estimation of the room. So we train with LiDAR data that is giving the ground truth of the room, and we expect to see in the output of the machine learning model rather like estimation, let's say. So in the end, in terms of evaluation, we will compare the point cloud output in output of the machine learning model and the original point cloud, which is given as a ground truth. And for evaluating, we will just measure using a conventional evaluation metric for point clouds, that is the chamfer distance, is basically quantifying the discrepancy between point clouds. It's basically taking the difference between the 2 point clouds and computing the distance between the points. In terms of dataset, so the dataset is available both in our NIST data repository and in the GitHub that we are hosting. And here there are some details that I write here for future reference if people want to have a small tutorial. So the type of file, the naming of the file is based on the type of file, whether if image that is not used for the challenge but is there, LiDAR of the channel impulse response, the channel impulse response, and then you will see the area number, that is 1 to 3, the different area of the receiver, and the receiver position from 0 to n-1. The different area will have different n, so different total number of captures. And then the file extension could be JPEG for images, PCD for LiDAR, and MAT for MATLAB file. In terms of MATLAB file, there is not much more to say. It's an 8x8 antenna array at the transmitter and receiver. So when you load the data, you are going to have a struct that is a MIME channel input response. That is, in this case, 64 by 64 is basically number of transmitter antenna by number of receiver antennas, and 136 taps in delays. If you want to reshape these 64 antennas, let's say, to be 8 by 8, is I use a conventional column-wise reshaping, conventional MATLAB, let's say, terminology. In terms of LiDAR file, also this is a pretty conventional Oyster file. The point cloud is unorganized and downsampled. We downsample it just because otherwise would be just too big to share, but the resolution is still pretty good. You can open it with MATLAB, Python. There are several ways to operate with that. And concluding, we offer at NIST a guest researcher position for the winner of the challenge. The ranking will be based again on chamfer distance, and yeah, the guest there will be 1 year guest researcher position available to the winner. And with that, I'll hand the floor to Yeshan, that is describing the solution that they provided last year, and the challenge is to beat the baseline solution.
Thank you, Steve. Thank you, everyone. Hope you enjoyed the presentation from Steve until now. I'm Ashwant Reddy from Samsung Research Institute in Bangalore. Our team 6G ISAC has 4 members: myself, Shubham, Avani, and Ashok. And we work on sensing applications that go beyond 5G. We were the last year's problem statement winners, and also runner-ups in the overall competition. In the next part of the presentation, I present the objective function and outline the baseline solution for the depth map estimation of the environment using 6G communication signals. So here are some of the snapshots of actual LiDAR point cloud and the predicted point cloud from our baseline solution. We can see that the ML model proposed returns LiDAR like high resolution point clouds, and the change in perception across location and orientation is nicely captured in the predicted point cloud, even though the transmitter and the receiver locations are unknown in the challenge. Now let's take a look at the problem statement and outline of the baseline solution. So this is the room in which measurements are taken, and we have a transmitter at fixed location on the left, and the receiver moving in different parts of the room as per the trajectories Steve has mentioned. And observation of the room changes with the receiver location and orientation. Here the challenge is to estimate the depth map of the environment at each receiver position using millimeter wave signals and an overlay of a machine learning model. In other words, we train an ML model that takes in MIMO channel impulse response as input and generates LiDAR point cloud as output. Note that we are only given channel impulse response as input. The location and orientation of these nodes are therefore unknown, making the problem more complicated. So now coming to the outline of the solution, the input RF data has a transmitter and receiver at a physically separate location, also known as bistatic mode, whereas commonly known as bistatic mode, whereas in LiDAR, we send and receive laser signals from the same location, which is also commonly known as a monostatic mode. So the pre-processing step that we introduce handles the deterministic aspects of transforming the MIMO channel data, which is in bistatic format to monostatic format. This makes machine learning model learning faster and more understandable. Looking at the input data at each location, we observed that RF data has lower resolution and fewer reflections, which is approximately 6,400 points, whereas LiDAR has both higher resolution and larger points of reflection, approximately 32,000. So at each location, our receiver location, we transform the bistatic RF data into monostatic format and then train the ML model by fitting it to similarly structured LiDAR ground truth. The first step in, so I'm going to detail the pre-processing steps that we follow before giving the input to the machine learning model. The first step in the pre-processing is to perform spatial transform on the input channel impulse response. This is done so that we can transform our data from an antenna space to angular beam space. The spatial transform, therefore, helps us get to the sensing framework from communication framework. On the right, you have a plot of matrix which I name HBeam for a delay, for a specific delay, where each entry represents power for a angle of arrival, angle of departure pair. So this matrix HBeam gives us power of reflections at points in the environment separated in distance by 17 centimeters and approximate angular resolution of 22.5 degrees across azimuth and elevation. And these resolutions are determined by the number of antennas we have and the sampling rate of the receiver. Now that we got HBeam, we need to transform it into a monostatic format. That is as if transmitter and reception occur at both occur at Rx, that is receiver. So the first step in this transformation is to find the line of sight path. So to find the line of sight path, we select the beam which has one of the following characters, that is higher power, lower delay, or tighter beam width. Since the line of sight information, line of sight path doesn't have information about the environment, we remove those entries from HBeam. But we store the line of sight parameters as they give the location and orientation information of the receiver, which will be used in the subsequent steps. Next, we remove the effect of transmitter in the matrix HBeam to get power map or power of reflections from a receiver perspective. We do this by projecting the angle of departure dimension to delay dimension, making it making the matrix from going from 3-dimension to 2-dimension. So the signal here, so the next step is to remove the effect of a transmitter. So the signal here shows the RF communication signal traveling R2 distance before hitting an obstacle, and then traveling R1 distance before arriving at receiver. So it travels R1 plus R2 distance before coming to receiver. So if we want to remove the effect of transmitter, we need to shift the delay of this entry in HBeam from R1 plus R2 to R1, so that it appears to arrive at Rx directly or receiver directly from the reflection point. To do this, we need to calculate the ratio between R1 and R2. In this triangle, which is made up of line of sight path and the current reflection, the angle of departure, delta AOD, is the difference between angle of departure of line of sight and of the current reflection. Delta AOA is can be defined similarly. Here we use the line of sight parameter saved in the previous step. And as you can see from this triangle, if we apply sine theorem, we can obtain the R2 by R1 ratio by taking the ratios between sine of delta AOA to delta AOD. Now we can present the entries in AOD dimension to appropriate delay to get power map from receiver perspective. In conclusion, we remove the effect of transmitter by projecting AOD dimension to delay dimension. The last step remaining is to scale the power so that the reflections appear to have traveled the receive path twice. So we multiply it with R2 by R1 square, and this ratio is already calculated in the previous step. And with this, we have finished the pre-processing where we have taken the channel impulse response in bistatic format as input and obtained receive power as output, which is in monostatic format, similar to the LiDAR data that is given to us to target. Now it's ready to be sent to the ML model. So the plot here shows the pre-processed data for a single receiver location. We see power at receiver at 64 different angle of arrivals, and in each angle of arrival we get power at 100 different delays, and this is the input to the ML model. So yeah, so we are defining the input and output of the ML model, and as seen in the earlier, the power of reflections at a receiver from 64 directions and 100 points in each direction. This is the input for the ML model, and this translates to 17 centimeters in range and 22.5 degrees in angle. And now I will explain the output for the ML model. Given output for the challenge is LiDAR point cloud of the room as seen by the receiver. One LiDAR point cloud approximately has 35,000 points, which are the coordinates of obstacles, and it looks like the figure shown here. And for the ML model training, input and output data is given for multiple locations across the room. And perception of the room as seen by the receiver changes with change in receiver location and orientation. Here are some snapshots of the output data across locations explaining this behavior. Setting receiver as origin, we observed that across locations, the LiDAR points are inside a bounding box with the minimum bound of -16, -16, -2, and maximum bound of 16, 16, and 2, where the units are in meters. And so we use a voxel grid as output for the ML model with these min and max bounds. With the voxel size of 0.25 meters, the dimension of the voxel grid is 128 by 128 by 16. And if you use higher voxel size, it decreases by half in each dimension. Note that 35,000 points of LiDAR point cloud fits into 13K voxels of the voxel grid for 0.25 meters. So higher the voxel size, the complexity of the model will be lower, but the resolution of the output will also be lower. So there is a trade-off here. And so why is this problem so challenging to solve? So there have been enough research on using camera input as image and to get a depth map, and also a few works on using high resolution LiDAR as input and radio signals as output. But in this problem, we have a more challenging situation where the input RF data has way less resolution than the output LiDAR data in terms of both range and angle. This is because LiDAR is at a higher frequency and also is guided by laser beam, while RF sensing is limited by sampling rate and number of antennas. And LiDAR gives more reflections compared to the RF sensor. And to talk in terms of numbers, the input dimension is quite lower than output dimension, and the ratio is approximately 3%, I by O ratio. And apart from this, for this challenge, the transmitter and receiver locations are not given as input to the ML model. So as far as we know, this is the solution is novel and the first of its kind. So now I will explain briefly the machine learning model we used. So here we have the pre-processed channel impulse response, which is basically the receive power, and it is fed to the dense layer followed by an upsampling layer, and then into 3 CNN layers to predict the voxel grid, and further then we map it to the point cloud data. We use the upsampling layer because the input to output dimension ratio is very less, approximately 3%. And we use the CNN layers because there exists correlation in reflections in the immediate neighborhood. So we use CNNs to capture that. So yeah, now I will explain the training parameters that we use. We use custom loss function, which is similar to binary cross entropy loss function with added weights for the labels. Higher weight is given to 1, that is when voxels are on, since in the output voxel grid only 13K voxels happen. So we train the model with 3,400 samples captured across various locations in trajectory 1 and trajectory 3. And testing data consists of channel impulse response from these 529 locations in trajectory 2. So we train this model with the Adam optimizer with a decaying learning rate of 0.0005. And so here are the snapshots I showed you at the start of the presentation, which is what we get from the machine learning model. And the model predicts a dense point cloud, which captures the change in depth perception across different locations. And we have seen the quality of the prediction given the difficulty of the challenge. Now we explain the quantitative evaluation metric of the challenge. As Steve mentioned, we use chamfer distance for measuring the discrepancies in the point clouds. Lower the chamfer distance, closer or similar the point clouds are. I'll explain the error analysis done in terms of chamfer distance across locations. So we have plotted chamfer distance for testing data, which is collected along the purple route. Transmitter location is at in the bottom left corner. Here, blue means chamfer distance of 1 meter square and red means chamfer distance of 9 meter square. We see that most of the samples are blue, which suggests the prediction is good for the room dimension of 16 by 16 by 4 meters. We also observe that from the figure that average chamfer distance across locations for the testing data is 2 meters square, while samples which are closer to the transmitter have a chamfer distance of 1 meter square. So we also did error analysis on the training data along the blue route for different voxel sizes. We found that the voxel size of 0.25 meters provides better chamfer distance of 1.5 meter square, whereas 0.5 meter of voxel size gives us 2.2 meter square. So the problem and the proposed algorithm are the first of its kind, and therefore can act as a baseline solution for the CS participants to build upon. And so these are the observations from the model. That is, it provides high resolution point clouds and captures the change in perception. Average chamfer distance of 2 meters square across the locations, and for the locations closer to transmitter, it's only 1 meter square. And so to improve upon these are few ideas. So we can use higher resolution input data, that is by using signal processing techniques like interpolation or other high resolution methods, and also experimenting with higher resolution output, that is by lowering the voxel size. And one can also experiment using multiple locations to estimate the depth map for a single location, that is using global training. So yeah, these are a few ideas that you can use to improve upon the solution. And thank you for the opportunity. And if you guys have any questions, yeah, you can go ahead. Yeah. So.
Okay, thank you so much for the presentation. Now we would like to go into the Q&A session. So I'd like to welcome Vishnu. Hi, Vishnu, and good evening.
All right, thank you. Oh, all right. Thank you so much. Yeah, thanks, Thomas, and thanks, Steve and Jason, for that presentation. First question is, Jason, do you provide this code for your solution as a building block? Is it open source? Can we look at it? Can the participants look at it and build upon it? Yeah.
I think so. I mean, I have shared the code with Steve, so we have to discuss how it will be hosted. So yeah, it will be shared.
Steve, you have comments?
No, I think it should be already available in the repo of last year's solution. Probably, I mean, if it's easier, we can just add it in the repo of this year just to have everything together. But I mean, it's already available. Yeah.
Yeah. Thank you so much. And I think I want to ask you, Steve, the chamfer distance. Why did you select this chamfer distance? I don't remember discussing this last year, but could you explain why did you select this metric and how is it related to the depth map itself? How did you arrive at this metric?
So it's one of the, probably the only metric that is used to compare different point clouds. So basically, one of the problem in comparing point clouds is that two similar point clouds that look, let's say, very similar, they might have a different numbers of points. So it's not really easy to compare, two different point clouds. So what this metric does is basically a weighted sum between two differences. One is basically assuming the estimated point cloud as, we'll say, the reference, and then at each point of the estimated, do the difference with the closest point of the real point cloud, but also you do the other way around. So you take the original point cloud as a reference, and then you associate each point of the original point cloud to the estimated, to the closest point of the estimated point cloud, and you take the distance. So it's a way to, provide a distance metric while taking into account that two different point clouds might have different points.
I see. Okay, that makes sense. Yeah, so I want to ask Yeshwant, did you use any particular reference for your solution? Are there some papers? Are there some existing work that you guys looked at when you solved? Can the participant for this year look at such references? Will it help them?
Yeah, so basically, at least for the pre-processing stuff that we developed on our own, but for the ML part, we did refer to a paper which talks about mapping radar to LiDAR. So that paper, we took cues from that on how deep it could be, or what could be the individual there. So we took references or inspiration from that paper. So yeah, I'll share the link, I guess. Yeah.
Sounds good. Yeah. I think you can upload it to your GitHub and we should be ready. About the pre-processing, I think it was quite interesting. Your pre-processing steps that you explained were quite interesting also. I want to ask about computation. Given all these steps, what was the computation requirements on your side? For training, especially for training, and where did you run it? You guys used your own GPUs or your own compute, or what are the requirements in terms of number of cores and number of hours, days, whatever? This will help us help the participant. Your answers will help the participant to understand what they are getting into. Obviously, the problem statement is quite exciting. I think it's quite worth it. And ITU does provide GPUs. So yeah, Thomas will explain that. But I want to ask your experience, please. Yes,
So we used our own platform. We have like remote servers where we can load the problem and train and test the said train model. And so it took I like this. It has been some time since we ran the code, so I can't give you the numbers right now. But it was taking like at least 5 hours for like when the whole thing, the training and testing, the whole thing. I'll get back to you about the numbers because I don't remember the number of servers we are parallelly loading, and yeah, those details I don't have right now, but I'll share them. And so that people can have a sense of how much time it could take. But yeah, as you already pointed out, NIST also has servers where people can run the models. So yeah.
Sure. Yeah. I mean, some ballpark figure is enough. We provide compute. So yeah, sure. And if any participant would like to utilize the GPUs, please talk to us. We will provide. I want to ask Steve a philosophical question. The TXRX locations. Well, if you look at it this way, Steve, your robot actually can figure out where it is. So I mean, it is easy to give the TXRX locations, no? I mean, at least in your data collection. Why it is not part of data? Why did you what is your take on it, first of all? Will it add value to the problem statement? And why did you leave it out?
Yeah, I mean, if you provide transmitter and receiver position, there is no real challenge because the receiver position is actually estimating always the same room. So if you it comes back to a simple geometrical problem because the room is always the same when it moves. And if you know exactly the position of transmitter and receiver, you can easily compute the room. However, I mean, it's in general the positioning indoor cannot be really provided in terms of GPS. You can have some network estimation which might not be that accurate and not enough, let's say, to solve this kind of problem. So I think it's fair to leave it out and trying to push, let's say, the boundaries of the algorithm.
Sounds good. Yeah, you are right, I think. Yeah, probably you're right. Yeah, I think the indoor versus outdoor. So yeah, that reminds me. So I think we discussed this last year also, this problem of indoor versus outdoor. Do you see similar solutions in the outdoor? Do you? I mean, we have had similar data sets. I think you know, in the mobility domain. So what is your take on that? Are the data sets and problem statements entirely different when it comes to indoor versus outdoor? So what is your opinion?
So yeah, the propagation is really depending on the environment. Already, it's not just indoor versus outdoor. It's just indoor in one room versus indoor in another room. The propagation is already different. And that's actually one of the motivation why we are providing the same data set, because at NIST we are collecting a lot of data. We have other environments, other measurements, and we could have provided new data, new environments, but we thought might have been difficult, to compare, for example, with previous year solutions. So before generalize a solution, we want to have really a strong algorithm that we are confident it might work also in other environments. So this is in terms of, this is for saying that different environments have different challenges. Now, moving outdoor in terms of RF propagation might be a bit easier, let's say, because there are less multi-path components. Let's say the RF propagation is free to escape, while in the room you have multiple bouncing. And one of the problem actually that the team had last year, that I'm aware, one of the problem was the fact that there are multiple components arriving at different delays and might give you a wrong estimation of the dimension of the room. You might basically see, if you just rely on the RF, that you have rooms of multiple dimensions using the same RF data. This problem shouldn't be that problematic, let's say, in outdoor environment. However, it's always it's not easy to say like this. I mean, millimeter wave propagation it's still a research topic. We are still doing, after many years, a lot of measurements. So yeah, I think the only answer is try and see what such an algorithm, machine learning model could, what result can provide also in outdoor environments.
Absolutely. Yeah. Thank you so much. Actually, your statement about research, actually, that reminds me of our discussions, early discussions with Nada and Tanguy and so on, right? Where is this research going? I mean, I remember our discussions around 3D map generation, and looking at my notes. So we had discussed about material template libraries, and you guys had brought up this such libraries and objects which were actually quite interesting. Could you tell us where is the future of this research? Where are you going? Where are you guys going with it? And in general, where the research groups are going with it? I know this problem statement is probably a small part of your research, right? So you guys have a bigger picture. I mean, you guys, if somebody goes back to our history and looks at our webinars, it's quite clear actually. You guys have a larger picture around this. So what's going to happen next year? So what is the future of this research, and what are competitors doing? What are the competing approaches to this? And in general, can you tell us where is the future of this research?
Yeah. So in general, at NIST, let's say we are more interested in the measurement in general of measurements, but in this case, measurements of the propagation. So we have been conducting millimeter wave measurements for years, characterizing the environment, as you said, indoor, outdoor. Now we have been integrating extra sensor, and the idea there is to use multiple sensors to have faster acquisition time, and because using other data we can speed up the process of the RF, but also more precise characterization of the environment, because as I was mentioning, for example, in the presentation, we see reflections, for example, in the indoor coming from the chair, from the table, from the projectors. And if we have only RF data, we somehow need to guess where is this RF coming from. Integrating with multiple sensors, we can make more informed decision to describe the propagation. So this is what we have done. So this is the bigger picture. And then we have application. For example, the challenge itself, it's an application in which we try to understand how a possible application would really perform using how an application could be designed using our measurement campaign. In terms of current work, of course, for example, as I was mentioning, we are working on the large umbrella of integrated sensing and communication, which does not include only environment estimation, but also presence counting, for example, understanding how people interact with the electromagnetic wave at millimeter wave, how they interact when they just walk, or even, let's say, trying to detect breathing rate and heart rate. So this is work in progress. And speaking of future work, our direction is to go even higher in frequency. So we are at the moment testing our new channel sounder at 140 gigahertz, and the idea it's let's say it's always our interest to understand how the propagation goes there. You ask about competitor. I mean, we are not the only one doing that, but the topic is pretty new, and I think we all need to team up together to, try to really understand the problem. Yeah, that's a little bit an overview of our work.
Okay. Yeah. Thank you so much. There is Thomas. Yeah. Yeah. That's our cue. Thank you so much, Steve and Yashwant, for the great presentations and the patient question and answer session. Thank you so much. Back to you, Thomas.
Thanks a lot, Vishnu. And I would like to take this opportunity to thank everyone who joined the session. It was quite interesting to see what is in line for the challenge this year. I would like to thank the speakers. Steve, you have been helpful with us for the challenge for the past 3 years. It's been amazing. And we are really looking forward to working with you on this challenge as well. And also, I'd like to thank Yashwant for coming up to help out with the challenge, providing the baseline. I know it's quite a lot of work, but you have put your time together. So thank you so much. And it's exciting to know that this year we have a guest researcher position, 1-year position that anyone can win. So good luck to everyone who is looking forward to working on this problem statement. I'm quite excited to see what will come out this year. So at this point, I would like to close the session, and please note that the challenge is open for registration. You can start registering today. I know there are already some teams who have already registered, so thanks a lot. And I would like to encourage you to send this information to all your networks. Make sure that many people can register, and should be a big challenge for this problem statement. And of course, on the ITU side, we are going to offer prizes, 1,000 Swiss francs for the winner as well, including also certificates, as we have been doing in the past years. So please work on this challenge, and good luck to everyone. We have more sessions in future. The next one, you can check on the AI for Good program page, but also we have the next problem statement that we're going to introduce in next week on 23rd of May. So we would like to see you on that one as well. And we look forward to everyone's participation in the challenge. So thank you, and have a good day to everyone. Thank you. Bye.
Thank you for participating in today's AI for Good session. We hope you've learned something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the eShop, and build your personalized AI for Good program. Let's shape the future of AI for Good.
AI is a powerful tool.
This summit can help ensure that artificial intelligence charts a course that benefits humanity and bolsters our shared values.